Okay. So on my clock, it's 3 p.m., which tells me that the webinar is about to start. So yeah, let's start. So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you a unique methodology of simulations of centrifugal fan, especially about CFD, FEA, and FSI, and also optimization and all the workflow around and associated workload. So, yep, hello everyone. So this is our 67th webinar, and together with me on the line is Radek Maca. So let's check the connection. So hello Radek, can you hear me? Can you see the presentation?
Hello Luboš and hello to the audience. I'm here and ready for the webinar. So
perfect. Okay, thank you,
great.
Radek. I'm glad to hear you. And yeah, so it seems everything is set up, and I think it's time to get to the action. So I'll just make sure you know that the webinar is being recorded, and the recording will be later made publicly available on our YouTube channel. So there are also a lot of questions usually associated with about the recording. So yes, the recording will be made available, and you can be sure you will be able to see it. Yeah, the webinar will take about 1 hour. Let's see what we can do. There will be like 3 parts in the webinar. In the third part, there will be a necessary introduction, which myself, I will show let's say a general introduction to the problem about what's on the table, and it's yeah, just necessary information. In the second part, there will be we call it hands-on part. Radek will show the real workflow live in how the workflow works in the software, what to do and how to do that, and how to evaluate everything. And in the last part, there will be Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. There is a special window where you can ask your questions, and we'll do our best to answer your questions. You can be sure that we will answer all of them. We will answer the most relevant and representative questions right here in the webinar. And those, let's say, more specific questions, we will answer them later via email, but you can be sure that all the questions will be answered. So that's for the organization of the webinar, and I think we can go into it. Okay, so let's start. So the necessary introduction. So our company name is CFD Support. We are located in Prague, Czech Republic. The company was founded in 2009 as a startup. And yeah, it's been a couple of years. We are doing well, and we are delivering services connected with CFD, FEA, and FSI, and also with optimization and aeroacoustics. Our flagship product is called TCAE. It's a comprehensive simulation environment where the users can simulate things and simulate fluid dynamics and develop their products based on the results. And yeah, TCAE consists of software modules, so it's not just one. You can view it as a couple of, it's a very coherent but more pieces of software, and it can be split into individual modules. We call them software modules, and each module has can be viewed as a standalone, which can be used as an individual software. It's very important because for this reason, TCAE is extremely flexible. So every user can create his own workflow that fits his own skills, experience, purposes, and also all the circumstances on his workplace. So the flexibility is certainly one of the biggest benefits of TCAE. So we'll show a little bit more about this later in the webinar. Another very important principle is there are no limitations on the number of users, on number of jobs or cores, and there are no hardware locks. There are no limits on hardware installations. So the users can use TCAE to the fullest to scale their resources. That's very important. Another important principle is TCAE is focused. It's focused primarily on turbo machinery, like rotating machinery and rotating machines, and external aerodynamics. We believe that if the software has to be accurate, if when it works properly, it should be focused, because we don't believe in general purpose codes. What's for everything is for nothing at the end. That's what we believe in. So it's accurate. It's also automated. It's perfectly automated. So it's the user who can decide whether to like dive into the details or use it as a black box. So that's another very important principle. So it's always up to the user what the workflow will be, how it will look like. And we also create a lot of benchmarks. So we test all the time TCAE again and again to be accurate, and we make sure it's accurate, and we are used to show to our users. So that's also another very important thing for us. And TCAE is also developed to be used to use the resources to the fullest. So it can be run remotely. It's perfectly designed to be run like on laptops, on PC, on cluster or cloud, and you can connect from home or from your office. The workflow is same everywhere in Linux and in Linux, in Windows, and so it's this. And another important thing is TCAE is based on open sources. So it's based on open source. So there are more than 60 open source projects included in TCAE. And on top of that, we have spent more than 40 many years of development in a team, which makes TCAE a huge project, where enormous effort has been spent to deliver this. And it's pretty big thing, because everything has been tested and created to work as a smooth workflow. And if I have a little advice for you, if you ever would be thinking about creating a new CFD software or new software for engineering, please don't do that. It's crazy, and it's so much work, and it's very big thing. Anyway, let's move a little bit. The current stable version of TCAE is 23.03. We released this version in March, and it's I would say it's pretty new. So it's a comprehensive simulation environment, so where you can 100% of workflow spent in the graphical interface. Of course, you can run it in the batch mode if you like. And we've spent quite a lot of time to deliver this current stable version. And of course, we are already working on the new version, which will be released in September or in October this year. And there will be, you can look forward to a lot of new features again, of course. So there will be extended support for remote computing. So there will be an option where you can disconnect the graphical interface from the running simulation and connect again and disconnect again. So it will be a pretty big thing, and we're continuing in the trend of flexibility about the remote computing. And perhaps the biggest thing in years is the new module. So we hope we will make it to till the 23.10 version. That there will be the first version of the new module called T-Base, which is big thing. Really big thing, because as you know, AI is disrupting field by field everywhere in the technology and everywhere around the world. And also the CFD and engineering simulations are being disrupted badly with this AI. methods because it's a really big thing. As you know, over the last from the beginning of our field, for the last 40 or 30 years, all the data has been, or most of the data has been erased and removed, and we have taken very little. We have taken very little lessons or very few lessons from it. So we definitely have to do something about it. We have to, our vision is we have to write down the results into special databases, and then we have to learn how to mine them and create knowledge bases. And our vision of the future of simulation engineering is that we will be much less simulating and much more mining the data, because it's a really big thing, and it's definitely happening, and we hope we are already working on it. The results are extremely great, better than we expected in the first place. It's extremely promising, and we'll be happy to show you in the next version, hopefully in the next version of TCAE. And this is of course just the beginning. And it's not just a chat GPT, it's something much bigger. Okay, yeah, I think it's time to move on, and I would like ask Radek. Hello, Radek. Yeah, once again, I'll make
Hello
you
again.
organizer. Yes, hello, and I'm handing over the presentation over to you. I think we can see your screen. Okay, so the
Perfect.
stage is yours.
Okay, thank you, Luboš. So thank you again, and welcome to the second part of this webinar. So in this part, I will show you the real workflow from very beginning. So I will start from really creating the STL geometry setup, the mesh setup, the simulation, and if we will have any spare time, I will show you a quick example how to create a simple T-opt simulation, and then we will conclude with a discussion or with a Q&A session. So just to quickly introduce into the problem, so maybe I will borrow, I'm at our pages, and I will borrow this T-opt module. So today I will be speaking about this particular case, but the general workflow holds for any other turbo machining application or even for any other CFD application. So what we have here, how the workflow looks like. So the standard workflow is that we need to have the input geometry in format of the external mesh or STL geometry. So in the T-mesh module, we create the computational mesh, which follows our needs to get the nice and desired results. Then we can enable TCFD module for CFD simulation, so to get the aerodynamical properties of our machine or our object. If we need to simulate also the FEAs, so some solid statistics like displacement or stress analysis, we can enable TFEA module. And if we are very eager for the acoustics of, for example, propellers, so we can enable also this acoustic module, which will give us some frequency domain properties of our rotating machinery. So this is the standard workflow, and if we enable T-opt, we can surround the standard workflow by the T-opt loop, which is also, let's say, pretty simple. So the T-opt loop includes the optimization or standard DOE. So for example, if we would like to know how the parameters of the explicit parameter list, let's say, we can impose the DOE, where we can define the explicit domain or implicit by some script which will tell us from some function or whatever how the parameters should look like for the simulation. Or we can go for the optimization. We can use our built-in optimization tools like golden search or direct method, or you can connect it to the external tool like Dakota or any other tool for the optimization. Then it will generate us the new point of the parametric space, and we can iterate this loop up until our objective function reaches our goal, and then we can see the final TOP report at the end of the simulation. So if we have everything perfect for the standard loop, so we have a perfect result for a CFD which follows our needs, so then only then we can apply the TOPT, because we need to know that the TOPT works with the proper results and is not influenced by any flaws in the simulation mesh or any flaws by the setup itself, which will give us the nonsense as a TOPT result. So going back to our case study, so you can find it also on our web pages in the case studies menu, and this centrifugal fun will be our target today. So if you would like to do the geometrical optimization, so the optimization of the geometrical shape of our input geometry, we need to have some geometry builder. So we need to have the software or piece of code which parameterize our model, and based on the set of parameters, it will give us the input geometry which we can put into the TCA workflow. So in our case, this is one of our older projects where we developed this parametric centrifugal fan in the Salome software, which we use pretty often for geometrical, let's say, adaptation or cleaning or whatever. But there are many other tools like FreeCAD or many other commercial tools. So we will use this one. So first of all, I will not go into much detail. So I will just take this geometrical tool, and I will create the first set or first geometry which I will use for starting the workflow from scratch. And then, because it will be ready to this type of geometry, then we can impose the TOPT loop and preset some optimization. So let's go for it. So I will start on my disk. I have created this webinar case here where I put the geometry builder. So it's written in Python, and it is read by Salome, and these two tools together will create us the input geometry in STL format. So I will quickly generate the geometry. So to run it, it is pretty simple. So I will just run my current Salome version. There is a run Salome executable, and I will give it -t to use a script, this build geometry. So this Python script is written is the input for the Salome, which describes the model and how to create STLs, etc. So I will just run it. So now the Salome will be opened, and the geometry will be generating. And this first variant of the geometry I will use for setting up the whole workflow. So if you use any other tool, so first generate the first set or some baseline geometry for which you preset the workflow you need, and then you can incorporate the parametrical study using the TOPT in your final workflow to get the optimized design or whatever you need. The optimization can be also applied to if you look for the best numerical parameters or the best mesh parameters. So you can also vary any parameter which TCA workflow includes. So for example, you can vary over the refinement at the particular place or the overall refinement, or you can also, for example, look for the best numerical scheme with respect of the optimization, or you can also look for the best relaxation factor to achieve to increase the speed up, or to speed up the simulation and find a point where it becomes unstable, so you can then also optimize in this way. So yeah, the options are almost unlimited. Okay, so now the geometry is already created, so we can see that in our geometry builder directory there is a new STL directory in which the STL parts which are necessary for setting up the simulation domain and simulation mesh is created. So basically we will just working with this set of STLs. Yeah, let's go for it. So I will open the latest TCA version, and let's start from very beginning. Okay, so I will create a new project. So I will create empty project. I will save it into my working directory. So I will go to the D drive, webinars, and this today's webinar and the webinar case. So I will name it as TCA case, for example. And here I will preset everything, and here we will be working with all the stuff. So first of all, we need to define and basically define the simulation domain and define the parameters of the mesh. So first of all, so in the T-mesh module, we can start from the up to the bottom over the menus and setting up the simulation. So the mesh output for now will be CFD mesh. If you maybe later we would like also to enable the FEA simulation, so then we can also add the FEA mesh for as a creation and as an input for the TFEA module. So let's stick for now with the CFD mesh. Here's the important button, use external geometries. So in the implicitly, everything, all the geometries are imported into the case, into the project, and will live with the project for next all the next steps. But if you would like to work with the optimization, so for each optimization step, we would like to have a new load the new variant of STLs after each optimization step. So you can imagine, like, after each step, the geometry builder is run again, so it will regenerate the STL into the same directory, and the T-mesh will automatically take the new set of geometry for the next optimization step. So for this purpose, we need to enable the use external geometry, so it will always go for the STLs to some external directory, which we will tell later in the CFD mesh setup. So this is the important part, and this check external timestamps. If it's mainly applicable for a single simulation without TOpt, so if the external STLs are changed after our simulation, then it will tell me that okay, something were changed and your current results are out to date. So typically this is for a single simulation without the TOpt. All right, let's go for the CFD mesh. So here in the first step, we define the rotation reference frame. So it's basically the axis of rotation. And here, this model, I think, is aligned with the y-axis. So the rotation axis is pointing to the y direction, and the origin lies on it. So I will set for both reference frames. So we need two, because one will be rotating and one will be static, and the transformation is usually the same for both of them. Typically, if you have the segment geometry, so we need to know the segment transformation, even it's for the stator part. So therefore, we need both static and rotating reference frames. Now let's go for the components. just to imagine how the geometry looks like. Maybe this is typical. Yeah, this is nice image. So the geometry domain, or the simulation domain, consists of 3 components, 3 regions. First one is just the suction inlet, then there is the rotating part, the impeller itself, and the third part, again the stator part, is a volute, or the spiral part. So we would need we need to create 3 components. So let's start with the first. So first component will be inlet or suction, so let's call it a suction. The reference frame will be static. And now the mesh input, because I'm not importing anything, because I check here use external geometries, I need to tell what is the input geometry or input directory to load the STLs. So I will go to our geometry builder and I will click on STL directory. So then all the STLs inside this directory is loaded into my table, and now we need to assign the patches which builds the first component, this suction component. Okay, so the first component consists of the suction inlet, which is the physical inlet. So you enable the given part by adjusting or by applying the particle type of the boundary. So first one is the inlet, which is the physical inlet into the domain. Then we have the suction wall, so we can set it as standard wall. And then we will have the outlet, and it's not the physical outlet because it's connected to the neighboring component. And for these purposes, so we have this interface suction to impeller part. We need to set it as outlet interface. So because for the interfaces where we know the direction of the flow, we can set if it's outlet or inlet. So for these purposes, we will set the outlet interface. So this is our first component. Let's go for the next one. So I will create new component. So I will add new component 2, and I will call it, for example, impeller or rotor. It's up to you. Reference frame, so this part is rotating. And again, I will locate the same directory with STL. So this file browser knows my last position. So I just click OK. And again, I can preset all the parts which belongs or which builds the impeller part. So here we have the impeller is split into the several parts. For example, here we can see that we have separately set leading and trailing edges, pressure side and suction side, which is then which is a good choice for setting specifically the refinement on each part. Yeah, because leading edge is a highly curved part which needs to have higher level of refinement to proper follow the shape of it. So we need finer mesh at this part, and on the suction and pressure side, because they are more flat, we don't need to have such a finer mesh. All right, so the type here, we have just the walls, but for example, I can enable turbo machinery specific parameters, which will allows me, or which enables more types, which is connected just to the turbo machinery applications. So now here we have the types of the boundary, like blade pressure side, etc., to better distinguish the given part. So for the leading edge, we have here blade leading edge. For pressure side, we have the pressure side. Automatically, you will see if you load it, or if you enable it, if you assign a type, then it will appear in the render view here under the CFD geometry item. You can get rid of it, or you can visualize it here in this pipeline browser. So let's continue. Blade suction side, blade trailing edge. Perfect. Then we can set the blade hub and shroud, and a few parts which are missing, or maybe just the inlet and outlets, right? So sometimes if you don't see what is happening inside and you would like to see if you assign all the boundaries, you can use, for example, you can click on the CFD geometry, you can click here on the display menu, and in the opacity you can set lower opacity to see what is inside. If you double click any geometry which is already assigned, then it will appear, or it will be highlighted in the render view. If you double click again, so you erase the this highlighting. And okay, so what I'm missing is the interface suction impeller. So this is the inlet interface into the domain. And similarly, we need to define the outlet interface. So it's impeller to spiral, and we will assign the type outlet interface. Perfect. So what I also like in this geometry definition phase, we can create, for example, to see the meridional contour of what I have already defined. So we can click on the CFD geometry, we can click on a slice and create, for example, slice perpendicular to the x direction, which goes to the origin. And now if I click apply, I can also see the contour of my current geometry. So which highlights the boundaries which I have already preset. Here I think it's possible also to change the coloring. Yeah, so each part is in this way. Yeah. So you can change the coloring of each part you have already defined, so it's more representative that each part has a different color. So let's finish the geometry setup. So I will add the third component, which will be the spiral. It is again the static reference frame. It's not rotating, and I will load the same directory. And let's define the rest. So here we have a spiral wall, so definitely we need to enable it. So this is the spiral wall, as you can see, and there is a lot of parts from the impeller, because the impeller is simulated as a solid, and is, for example, this geometry is ready to the FEA analysis. So we have real the solid. Sometimes for the simplifications, the solid is shrinked to the surface, so there is no this solid part, but this is more complex model. So we need the external part of the rotor is included into the spiral. So therefore we have this, for example, spiral impeller hub part, so we can define as a hub. And now we need to be careful because this is the part of the hub and hub is rotating. So we need to set the reference frame locally as rotating. So this can be done for all rotational symmetrical parts, which are part of the stator component. If this part is not rotationally symmetric, then it must be included into the rotational part. So for that purpose, you would need to change the topology of the rotor part. But in this case, we can set it as a part of the stationary spiral component. Let's continue. So again, impeller hub trailing edge. So I think we can still define it as a hub, and you can see it's this short part. So again, if we have this part separately defined, so we can impose higher level of refinement for better mesh management. Let's finish it. So here we have the shroud part. So you will see that this is this line. Again, shroud trailing edge and shroud leading edge, which is at the beginning. I think here, yeah, you can see this part. And what I missed is to set all parts which belongs to the impeller is rotating. Okay. So what is missing are the interfaces, so spiral outlet. So we have no additional components. So this is the real physical outlet. So simple outlet type we will define for this part, and the interface impeller to spiral is the inlet interface. Great, and I think, because I'm not sure if the spiral wall includes also this part. Yeah. So what we can do, so if you go to the multi-block inspector, you can get rid of all parts, and maybe it will be nicer for this slice part. So if I click on the slice, and I will enable only the spiral part, so you can see that this contour here is missing. So I need to include this suction wall part also for the spiral to define this internal wall between the, let's say, spiral wall and the inlet into the impeller. So suction wall is here, and I will click here. Great, and now I think I can see nice and closed contour which defines me this spiral component properly. So I will save my current setup. So these clicks defined the boundaries, and now we need to define the parameters of the mesh. So first of all, what I can start with here, the components map shows me the topology of connection of the components. So because in general the topology can be pretty complicated, each component can have several outlets and inlets, and these outlets can connect the different components. So explicitly we need to connect each component to its physical neighbors. So let's start with the component 1, and the connection of components is done by right click on the interface type. So if I right click the mouse, there is a list of all available inlet interfaces. So the suction needs to be connected with impeller. So there is only one inlet interface on the impeller side. So I will click on this. And now we can see that suction is connected to the impeller. And similarly, I need to do for the component 2, because the connection is automatically, so the outlet is connected to the inlet or vice versa. So if I click on the inlet interface on the suction, I can see that it is already connected into the suction. So this two-way coupling is done automatically. And for the outlet interface, I need to do it for the spiral part. And now I can see the nice connection from the inlet to the outlet, yeah, which is the first control I can do if all my components are connected. Okay, so this was the connection. So I will click again save if something happened. So I would like to have everything saved what I have preset for until now, and let's continue. So we created the patches, we created the connection. So now for mesh definition, I need to do, for example, the steps of defining the internal point, because the meshing tool is SnappyX Mesh, and you can mesh the geometry from inside or from outside. So this is the case where I would like to mesh the components from inside. So therefore I need to put this internal point into the middle of my component. So when I click, you can put it manually, or you can place it via GUI. So I will enable this show internal point as sphere with radius, which is just for the visualization purposes. So I will make the visualization radius smaller, and basically the point is to get the point inside the component. So you can see that now it is in the section. Great. The same I need to do for the component 2. So again, show internal point, make the visualization smaller and put it inside the impeller. Yeah, so I think we are there. Great. And the last component is the spiral, and again I need to place the point inside the spiral. So for example here, so yeah, perfect, is inside. So this was the definition of internal points for each component. And let's start with setting up the mesh refinement. So SnappyX Mesh works that you first create the so-called background mesh cell size, so hexahedral background mesh, which amongst or which includes all the STLs, the whole component, and then you define the size. So I will define each cell size. So the largest, you can understand it as the largest cell in the mesh as a cubes. And let's start. Okay, so I will set as 10 centimeters. Okay, I think it's too large. So now, yeah, the playing with the mesh will be for several hours. So I would like to create some rough mesh on which the simulation will be fast, but also, yeah, we can't expect a very good accuracy. So from the simulation time point of view, I would like to create as coarse mesh as possible, but which describes all the geometry parts, let's say, with some degree of accuracy, let's say. So let's try to set the 5 centimeters, the cube of size 5 centimeter, which will be okay, I guess. So for the component 2, so show background mesh. What I usually like that for the most important part or most important components, for the important components, I usually set or suggest setting smaller cells, so finer cells. So instead of 5 centimeters, so I will set 2.5 centimeters. So usually I double or divide by 2 with respect to some based cell size. Because if I set, for example, 5 centimeters, you will see that, for example, on the outlet interface, I will have just 4 or 3 cells, which is pretty coarse mesh. So to have it more fine, I will double the count of the mesh or in each direction. So I will make the size of the cell half compared to the neighboring component. And the same for the last component. So cube cell, and again, because it's large, I will set again 5 centimeters. All right. So this is the background mesh cell size. And now I can play with the refinement at each part of the geometry. So let's make it coarse but nice for the eye, let's say. So for the inlet, I don't need to have any special refinement for the inlet. For the wall, let's say I will set level 1 to have a little bit finer on the walls. And for the impeller interface, because on the interface there is a connection and the data are communicating with these components via some methods, arbitrary mesh interface or mixing plane. So usually I would like to have finer refinement for better accuracy, and mainly, for example, if the interface is curved, yeah, so here is more flat, so it's pretty okay. But if for highly curved interfaces, you need to have finer refinement to have better accuracy for example, mapping the values of each quantity from one side to the other side. So let's say, okay, it's more important, so I will set level 2. For the component 2, on the inlet interface, because I would like to usually follow the same degree of refinement for connecting interface. So I will set for the inlet interface level 1, because the background mesh cell size is of half size compared to the next compared to the neighboring one. So level 1 will correspond to the level 2 on the component side suction. All right, and the same for the interface imperative spiral. I will set, for example, level 2 because it's more curved, so I would like to have more refined interface or patch. And the rest, because I would like to have rough mesh, so I will set hub and shroud and the same suction side and pressure side to level 1. And the leading edge, I think here we have it has the thickness is 1 centimeter, I think. Oh no, 1 millimeter. Oh, I am not sure right now. No, I think 1 centimeter. Yeah, 1 centimeter. So I will set the level of refinement because I have 2.5 centimeters to capture, to have several cells here. So I will set level 3 for the trailing edges. And the last part is component 3, which is the volute part. So again, so inlet to this part is here, and because the level of on the impeller side was 2, but I have a coarser mesh here, so I will set level 3 to have the same level of refinement. And again on the hub, shroud, and the wall, and the spiral wall, because it's not flat, yeah, it includes also this tongue and the edges. So I will set, for example, level 1 is a minimum for the flat surface and level 2 for the curved parts. And the rest, yeah, the trailing edges has the similar size like the blade thickness. So I will set level 4, which correspond to my same level of refinement for the leading edges in the impeller side or at the impeller side. So suction wall at this part at the suction side. So I will set it as 1, sorry, not 4, 1, not 41, just 1. All right, so okay, so I think we have preset everything what we needed. So I will save my setup, and maybe I forgot to speed up the generation. I can set the number of processor. My computer has 10 physical cores, so I will set 10 cores for the simulation. So save again, and now I will click mesh all, and let's see if I preset all the parameters properly. All right, so the first component is finished. It counts just 8,000 cells. So let's see it. So I can, for example, split this render view, or I can create a new render view. Here, create new render view. Now I can click show mesh, and what I need to click on the eye next to the CFD mesh, yeah, for the resulting mesh visualization. So here, the representation, I can switch to surface with edges. So this is my topology of the mesh. Yeah, so I think it will be okay for our case. And let's wait for the other components. So now the impeller is done. It's more refined. It counts how many cells? More than 100,000. Just focus on the edges. Okay, I think it's somehow roughly catches the curvature here. So let's stick with it that it's okay. There are no big flaws, no zigzag shapes or holes. So I think it's okay. And the last part to visualize is the spiral, also looks okay. And for example, just to see the topology inside, I can make a slice again. So I can apply the slice in the middle, apply surface with edges, and yeah, just to see the topology. All right, so yeah, I think it's okay for our test case. Of course, the accuracy, we would need much more level of refinement in this place. We would need also the inflation layer to create to have better accuracy. But for now, I think this mesh is ready for the simulation, but we can't expect any precise results. All right, so when I am satisfied with the mesh, we can move for setting the CFD simulation. So I will enable the TCFD module, click on the module, and let's quickly preset the simulation parameters. Simulation type, this is the centrifugal fan, so I will set it to fan. So this will, let's say, tailor some parameters and mainly the final report to the fan application. So we will see the specific parameters which are relevant for the fan application. Let's go for the time management. We stick just with the steady state simulation. We will simulate just one speed line. It means constant or single rotation speed. So just 1 point, one rotation speed. Speed line points, because we would like to apply for the optimization. So let's say we would like to optimize this centrifugal fan to the particular volumetric flow rate. So I will keep just 1 point. Point iterations, I have coarse mesh, so I think 500 will be enough. So again, this depends on your application, on the physics inside, on the mesh refinement, how many iterations are needed to reach the convergence. So let's stick with the default one. Physical model, because the flow is slow and there is no high pressure ratio, so we can treat it as incompressible flow. I will use the fluid default, so it's this is the air properties at 20 degrees Celsius. Multiphysics, I don't need any specific multiphysics here. Turbulence, I will stick with the default one, K omega SST turbulence model. And the rotational frame speed, so the rotating one, so the rotating component will be really rotating, and I will set 3000 RPMs, which is the speed I would like to simulate for this fan. And again, if I get rid of the CFD mesh, what we need to take care is the direction of the rotation. So it follows right hand rule. So the positive direction is this one, but I need to run it in this way, right? Because this is the leading edge. So it's negative direction. So I need to set it as negative, this number to rotate in this direction. For the solver, again, here I can set 10 processors, numerical order. I will set to second, so I hope everything is preset properly. So usually when I start a very new project, I usually stick with first order scheme, and if everything works, if the simulation converts well, then I usually switch to second. Runtime evaluated quantities, averaging window, which averages me this steady state solution, which stabilize the integral quantities if some oscillation occurs, which can occur for the turbomachinery applications. So I will stick with 100. Let's see after the simulation if it is enough. Efficiency probe. So this is the part from which I would like to evaluate efficiencies, which includes the total pressure differences, torques, and so on. So inlet, I will take as the real inlet, and outlet as a real outlet. You can shrinking these evaluation probes just to, for example, the rotor part if you want. And here I need to click on all batches which I would like to include into the torque evaluation. So basically I would like to have all rotating part which create friction and so on into the torque evaluation. Here I can define some forces and probes to see, for example, particle value at each particle position in the simulation domain, or the forces, but for example axial forces and so on are automatically evaluated from the torque patches, so I don't need to add any other force probes. Here wheel diameter, which is needed for some formulas specific to the fan performance parameters, and this fan has 1.5 meter in diameter, so I need to define it here. Convergence check, so these are the quantities which, if this, for example, I usually set if average efficiency oscillates less or changes less than 0.001, so it means less than 0.1%, then the simulation is stopped. So I will stick with this. Here are some advanced under-relaxation advanced parameters like under-relaxation factors, some linear solver accuracy and so on, but you can keep it default. In scripting, you can define some, let's say, user-defined function which can somehow tailor some part of the workflow to your needs, which are not explicitly available in the workflow. And now boundary conditions. So let's go for flow rate. So I will set volumetric flow rate at the inlet, and I would like to simulate 10 cubic meters per second. Turbulent quantities I would like to set using the turbulence intensity and hydraulic diameter. The inlet diameter is, I think, 0.75 meters, and reference velocity something like 20 meters per second. So it's just for the initialize the turbulence quantities at the inlet and inside the domain. At the outlet, I will set the fixed velocity. At the walls, I will use standard wall function because I have no inflation layer, so the Y plus will be maybe pretty high here, so there is no need to incorporate the low Reynolds wall function. So I will keep everything in the standard option, which is standard wall function, and all walls as friction walls, so no slip wall type. Interface conditions, because I have no segment, I will keep as arbitrary mesh interface. In CFX language is, I think it's called frozen rotor or something like that. Initial conditions, I will initialize the turbulent quantities with the inlet values, and pressure is 0, which is the reference value at the outlet, and the velocity, for example, I can set, because I know this, that at the inlet we have 20 meters per second, so in Y direction I can preset 20 meters per second, but usually this is not important for cases which converge well. For example, for compressors, sometimes you need to set the proper value, at least the direction of the flow. Okay, the post-processing. So here you can adjust the report. So you can set the parts of the report or sections which you can see in the final report. Here are some units you can choose. You can add some additional data. If you have some data in CSV file to compare with, you can put it here. You can evaluate some automatical visualization like blade-to-blade view. So you will just say which part of component you would like to unwrap and show the blade-to-blade view on it. Here you need to define what is the hub and shroud for the transformation purposes. So the algorithm needs to know how to unwrap the wheel, and the fields you would like to visualize. For example, what is nice to see is relative velocity streamlines, and the span is relative position between hub and shroud. Sorry, so it's just in the middle, and the meridional view, and I would like to see static pressure, for example. There are some other two options. You can write the result into the CGNS format or write surfaces to the later usage or whatever, or sample. You can have the values on specific patches for any other post-processing purposes. So let's start. Let's try to simulate it. So I can click on this check button to see if there is no misprints or some incompatibility issues. It seems that not. And now I can just check if I set 10 cores for the simulation. So yeah, 10 cores, okay. So now I can again run all because the mesh is already generated. So these steps are skipped, and directly it will start the simulation. So let's see if I set everything properly. So this window shows you the residuals, and by switching the views you can open new render view, and here in the pipeline browser you can enable the quantities view. Am I there? Oh yeah, here what I did, maybe again. Oh no, render view, I need the line chart view of course for the plot generation, and now I can visualize the quantities, and in the display I can choose any quantity I want. So for example, I would like to watch the efficiency, and I would like to get rid of the mass flow. And now you can see the instant values of the efficiency and residuals to see the convergence runtime. Okay, so it's almost 4 p.m. So let's maybe I will wait for the results, and maybe the setup of the TOpt we will skip for today's webinar, because the next webinar will be focused only on the TOpt module. So then we will have time to discuss all the TOpt workflow and all the parts of the TOpt into more detail and discuss it. Yeah, within I think 3 weeks at the end of the May. So maybe it's not necessary to show you today. So basically, this workflow I was able in some a priori knowledge to set it within 40 minutes. So the workflow works very well. It's easy to use, and if you get familiar and some experience, then you can be very flexible and and yeah, very efficient in your work. So let's wait for the report and for the result, and maybe meanwhile we can touch the TOpt, because I have prepared one example of the TOpt report. So at the end of the TOpt simulation, you will see report like this, which summarizes the TOpt simulation. So there is there is information about what you have optimized, how many optimization loops you have done, which parameters were optimized or used for the optimization. Then you have table of all the values. So for example, here you have the parameters which were changed, and here are the target quantities. For example, delta total pressure, efficiency, power, and optimization function, which you can build as you want. And at the end, everything is summarized in the nice graphs where you see the progress of the optimization. For example, the efficiency looks like this, and the optimization function, I think, is the direct efficiency. So you can see the progress of the optimization algorithm and how it goes to the best efficiency point, and then you have the summary of the best efficiency point, and then you can compare how the dependence of each parameters to the optimization function, and you can compare it, and also in this 3D graph how it behaves. But we will speak about this into more detail in the next webinar. All right, so the report is generating. We can see that the simulation is done. You can anytime open the data. Here you can click show the results. Right, apply. And you can follow the pressure, velocities. Again, you can make slices. You can make visualization of streamlines. You can do basically what you want. So it's based on just playing with it and get familiar with the preview tools, and then you can visualize what you want and to have really nice visualizations. All right, and maybe final part is the report. So at the end you will see the report like this, which summarizes the CFD simulation itself, and this similar report you will also get for the acoustics module, for the FEA module, and the workflow still remains the same. So for the FEA you will just input the STL of the solid part, create a mesh, preset the FEA parameter, which are much more simple than for the CFD, and get all the results you want. Yeah, so you can then list over each quantity, and for example at the end you can also see the blade-to-blade view, so the flow analysis, flow pattern on the blade-to-blade view, or the pressure distribution on the meridional average, which are meridionally averaged at the impeller side. All right, so I think I lost all of my time which I got, so I will conclude here, and I will give the presentation back to the Luboš to conclude and to summarize this webinar and to open a Q&A session maybe. So Luboš, are you still there? Because maybe I was more late than expected.
Yes, I am, Radek. Yes, I am here. Yeah. I was waiting. I wanted to give you enough time and also make you scared a little bit. But yeah, of course.
Okay,
thank you,
for
Radek,
your patience.
thank you, Radek, for your presentation. It was great. It was very informative, and yes, sometimes it's a little bit more detailed, and I hope the audience understands that it's you do it just for the first time, and then you just reuse what is already preset in the project, and it's definitely not necessary to do all the things from the scratch every time, right? It's always a matter of let's say cloning of working existing projects. Okay, so this was the example. Yeah, we would definitely like to invite you for the next webinars, because this webinar was specifically dedicated to the centrifugal fan and its let's say settings. The next webinar, which will be on May 30, I think, there will be an axial fan, but we will definitely be focused on the optimization. So the next webinar will be more about the optimization. So definitely we will do much less of setup and much more about the optimization. So we are already looking forward to it. Yeah, and now it's time for the quick Q&A session. So I would like to ask the audience to ask your questions. We'll be happy to answer some of them, and yeah, that's what's going on at the moment. So we will give you some time to write them the questions down, and let me see what we have. Okay, so Radek, when you see a question you think we should answer it here, please go ahead. I'll only say that, yeah, typical question, yes, the webinar recording will be available on typical place, and there's also an automated system which sends you an email. It's to the same email ID which you used for the registration to the webinar. So yes, the recording will be available. Also, Gokul is asking how to find the performance of the centrifugal fan. I think Radek showed it just in the latest part of his contribution in the report, right? So there is a relatively detailed report. Every simulation run has its report where you can see all the details: when, was it simulated, what was simulated, all the possible results are written down.
Okay, just maybe let me show some example. Just to add that you can also simulate more flow rates, so you can get the performance map into one simulation, right? So the simulation was just for one point, but you can imagine that you can also set different flow rates, and after that you will see, for example, the efficiency map like this. So for different flow rates at the fixed RPMs, you will see the efficiencies. Yeah, so because CFD will give you the answer to the preset condition, so you will set the bunch of conditions, and the CFD will give you the answers for the efficiency, power, or what you want to see. So this is available automatically in the simulation. Yeah. Right.
Yep. Yeah. Thank you, Radek, for this. There's another question. Yep. Also the efficiency can be found there. There's a question, a good question, typical question from Gokul is whether it's necessary to use steady state, or whether maybe a more sufficient would be the transient simulation. I'm rephrasing the question here. Yeah, so listen, and it's always a question whether to go to transient or stick with steady state. Normally, at standard turbo machinery, the steady state simulation is so much cheaper than transient in terms of the resources and of course simulation time and everything, so that most of the people most of the users still use steady state. Transient is sometimes necessary, but if it's possible, every time when if it's possible to avoid it, people use steady state because it's so much cheaper. So you can make it. I always say it's roughly by like 10 times cheaper in everything, in time, resources, simulation resources, and everything. So it's really a big deal. So this will be the reason why steady state still rules everywhere in turbo machinery. So yeah, Charles is asking, but I don't understand this. Answers full and working storage. Okay, so we will deal with this via email. And also Bistrik is asking, could you make TCAE case studies available for TCAD module only? Yeah. I know what you mean here. Well, we'll get back to you via email again, because you can switch it off, but maybe it's not a complete. Okay, Radek, I think this would be it. I can
agree.
Any questions. So I guess we should conclude. So I'm taking back the presentation. Yep. And so yep, here are a couple of those who already share our visions with us, and we believe that there will be more of you. And this would be really it. I would like to thank you for your attention. Maybe the last sentence, Radek.
Just let me thank the audience, and we are looking for the possible discussion or to meet you at the next webinar. So thank you and enjoy the rest of the day.
Okay, so thank you everyone. We will leave you with that, and bye bye for now.
Bye bye.